시작할까요? Good morning. Yeah, this is Seokcheon Lee. So welcome and thank you for joining us. I'm happy to announce the CQUeST Group 2 Workshop 2022. This workshop is organized by the Group 2 of the Center of Quantum Space-Time at Seokcheon University as an annual workshop starting from 2021. The goal of this workshop is to bring the experts in the relevant areas of research of Group 2 is cosmology, modified gravity, string theory, and black hole physics, and astroparticle physics phenomenology. This year, we plan to invite prominent experts on cosmology to provide review lectures and opportunities for graduate students and experts in other fields to enjoy and learn. 4 experts will give you a total of 8 review talks, 2 times each. Okay, let's go. Let's get started the session. The first speaker is Professor Seokcheon Lee at Seokcheon University. Will give a review talk on Big Bang and inflation. Professor Lee, please go ahead.
Okay, yeah. Thank you for nice invitation. And first of all, hello everyone. Yeah, nice to meet you, even though it's online. And yeah, because CQUeST continuously provide a nice lecture series and workshops, and fortunately this time is for the cosmology. And so there's 3 more nice lecture. So I just need to briefly mention introduce some fundamental of the modern cosmology, including the Big Bang and inflation, and also as a project from the inflation model, we now in modern cosmology we can predict some observation. So I try to provide the connection between theory and observation based on the Big Bang. So let's begin. So as a review talk, I will try to provide the introduction, some detail about how one can get the robot-to-work metric, which is the only known solution so far as a dynamical solution of Einstein equation, and which is based on the cosmological principle and so-called as a bias postulate, which will provide us the cosmic time. So today, yeah, I have some new opinion about the robot-to-work metric, but I will just adopt the traditional way. But I briefly mention what's the problem of the traditional metric, robot-to-work metric, which is based on the modern cosmology. And based on the robot-to-work metric with the material, which is we dealing with the thermodynamics based on the adiabatic condition, then the solution of the Einstein field equation became a so-called as a Big Bang model, which means the just expansion of the universe, which is quite against our intuition, and also quite difficult problem because in general relativity is a local theory, and if someone want to introduce the global solution, including the dynamical one, then we should have some assumption, which is a bias postulate. And even if we adopt that one, then Big Bang model start from the cosmological principle, so-called homogeneity and isotropy of a 3-dimensional space. And it should have the based on the homogeneity and isotropy, which is also coming from the adiabatic condition in matter part. But if we just have the Big Bang model, then we cannot explain why universe is so uniform and isotropic. So that's the so-called as a Big Bang problem. And in order to solve those problems, one can provide something different from the standard Big Bang, which is one way to solve is the so-called as the inflation model, the superluminal expansion in the early universe. And Yamaguchi-san will talk about the alternative models, not directly related to the early universe, but he will talk about something related to that. And then one solution, I just adapt the standard one, which is the most popular nowadays, is the inflation. And this one also will be covered by Professor Kong, so I will not talk about too much detail. But if we adopt that one, then that is coming from the quantum state of a scalar field, which is actually the Gaussian distribution. So one can talk about the stochastic property of the fluctuation, which will give us some consequence and make the cosmology as a predictable theory. And we can compare with the current observation, which will be covered by Professor F.B. So yeah, CQueST nicely organized the series of the lecture, which are all related to each other. So you can also refer to some details from the other nice lectures. So today I need to talk about the cosmology, which is the main topic. But cosmology is just the one part of the solution of the Einstein field equation, which is based on the general theory of relativity. But basically, general relativity is a local theory. And so the maximum range of people can use the Gaussian normal coordinate based on there's a one point of the manifold. One can choose the one point and make the tangent space around that point to make the Gaussian normal coordinate to describe some local behavior to make that one as almost like the Minkowski space. So, and in that case, gravitation is not a force, but we can interpret it as a geometric theory. So just one can show that the shortest distance due to the given structure and geometry of the space-time, one can describe the path of the particles, including photons. And Einstein field equation is derived from the general relativity, and this Einstein field equation is a second order nonlinear partial differential equation. So generally it's quite difficult to solve, and there's no general solution, especially including time. So far we only have a few solutions. So it's better to say we say the Einstein field equation instead of just a GR. So Einstein field equation have only few known solutions. And most popular right after the Einstein theory is the static solution, which is a local solution. That's the black hole, Schwarzschild, or stationary case is a Kerr solution. And Einstein himself in the 1917, he also proposed his static universe solution. And this is global but static solution. So it's difficult to say global because time, even though he introduced the time, but it's no changing based on the time. So it's not a dynamic solution, but it's a static solution. But main difference is he want to describe the not only local solution around the black hole as a specific solution for his field theory, field equation, but he want to describe his field equation for the global structure of the universe. That's the first solution. So at that time, he also assumed that the spatial, three-dimensional space is a homogeneous and isotropic, which is so-called as a cosmological principle. But so his metric itself is okay. He especially in modern language, he especially adopted the closed universe because he assumed that the universe is filled with ordinary matter, including the photon and the baryon. So it's a closed universe. So metric itself is including like a kr square in the radial direction and including the four-dimensional, the solid angle term. But he didn't including the dynamics of the universe. So he rescaled that one with the so-called some scale factor, but it's a static. So it's a constant value by adding the time term. So that was his solution. But So as a metric itself, it's okay. But the problem is when he plug back his equation, this metric into his field equation, then to solve the Friedman equation, then it's inconsistent. So metric itself is fine, but when you plug into the field equation, it cannot, the velocity term and the acceleration term is give us a different contradiction prediction. So that's why he need to introduce the so-called as Einstein cosmological constant, which is vector 2 smaller than the bigger than what we propose nowadays. But then that's the reason he need to introduce the cosmological constant to satisfy his static solution to satisfy his field equation. Later on, and it takes about 14 years for the Einstein himself to adapt to the dynamical solution. Because if someone solve the Friedman equation, elementary equation, then the consequence is the dynamical solution. So so-called as Einstein Friedman equation is published at the 1931, and then that is based on the Robert-Walker metric, which is not only adapting the three-dimensional spaces cosmological principle, homogeneous and isotropic, but he also need to introduce cosmic time. So when you say the Robert-Walker metric, that is including the cosmic time, that is the global time, and the co-moving spatial element, which is not changing based on the time, is constant. And then only dynamics is observed is in the scale factor, so-called scale factor, which is A is not constant, but is function of time. Then now there's some problem about the C definition. Okay, I will get to that slightly. And so when you say modern cosmology, then we adapt the metric part term, Einstein tensor term by the Robert-Walker type metric. This is only one solution, known solution, including digital is also the same form as the Robert-Walker after we doing the coordinate transformation. So Robert-Walker type is the only known solution, dynamical solution of the Einstein field equation, the global solution. And then the right-hand term should be coming from the dynamics, thermodynamics, which is based on the adiabaticity, and as a consequence, we have the Big Bang. So let me briefly, because short of time, I cannot go to too much detail, but as we say, Einstein's static solution is based on the three-dimensional space homogeneity and isotropy. So at a given time, one can adopt the killing vector for the rotation, for the isotropy isometry, and then for the translation invariance, we can have the homogeneity. So translational killing vector, we have three killing vector for translation symmetry. And then for the rotation, to cover the isotropic, we have an additional three killing vectors. So if we adapt those killing vector to the metric to make the killing equation at a given time, because the space-time is homogeneity and isotropy we're talking about at a one given time, then by solving the killing vector equation, then we obtain this form. And in here, A, scale factor A and the speed of light C is both constant. Is given at the measured at the given time at t equal TL. And this part is the closed universe. So that's Einstein, what Einstein adapt. You can put K is a 0 or negative based on the flat and the open universe respectively. Then what happened, this one, it can be followed by the photon, that means null geodesic. This type is same as a Minkowski type. Only difference is conformally this is flat. So this is you can think this picture as the Minkowski type. So along this line at the t equal 1, TL and the TL plus dt, there's a slightly changing in the time, then you can regard this hypersurface, two hypersurface with the dt make the Minkowski type space. So you can apply the special relativity where we can define the speed of light. In general relativity, usually, because it's difficult to provide the global time, only the Gaussian normal coordinate, one cannot define the even speed of light. But in robot-walker metric, at each time, we can define the speed of light as the CL. And based on the null geodesic at t equal t1, then speed of light is nothing but AT1, and this sigma, which is so-called homogene separation between two galaxies. In here is A and B, galaxy A and galaxy B. They following their one trajectory, world line, which is always perpendicular to the hypersurface, given hypersurface. That's the so-called Bayer postulate. So their proper time is the same as their cosmic time. So time is always perpendicular to the hypersurface to make the Minkowski space. So one can define the speed of light on that surface. So at the T1, C1 is nothing but AT1 multiplied by d omega divided by dt. This is not a differentiation. This is just a deviation. So one can say physical distance at T1 is given by AT1 multiplied d sigma. One can expand this idea to the t equal T2, then at that time, the photon between the two galaxies, A and B, their null geodesic is given by, again, the null geodesic. But C2 in this case is now have a different factor, AT2. So now physical distance traveled by the photon at T2 is different from the distance in the T1. So that's why C in the robot-walker metric cannot be constant. If you wanna, Einstein himself, he put the A as constant. So it's okay, C is constant because the physical distance does not change it. But in robot-walker metric, when people allowed the dynamics of the A as a function of T, then C should be also the function of T. Otherwise, it's inconsistent in the expanding universe. C can be constant, only A is constant. So that's the different from the traditional way, and which is not adopted in the community yet. And I still struggle with the journals, and then you will see. So today's topic, I should adopt the traditional way where C put as the constant. But this one is not an end of the story. If I allow the C as a function of time, then we should plug in back to the Einstein field equation, which is consistent to the field equation or not. Then there will be some adiabatic condition should be satisfied, and then we see the different additional changing should be happen compared to the traditional method. But that's not the scope of this lecture, so I will not cover about that. But all the history in here is actually given by these nice textbooks, except when they adopted the Bayer postulate, they just allowed the A as the function of time without allowing the C. But that gives us the contradiction already. So it should also C also should be function of T. That's not be done yet. So it's what I give in here can be arguable. So today I will just adopt that C is constant, but A is still allowed to dynamic.
Very naive question. I mean, you seems to be saying that if the scale factor A is a function of time,
Mhm.
also the C should be a function of time. But
Exactly.
however, by redefining my time T,
Mhm.
can I make a C always constant, like
Yeah.
1 or whatever?
There's some textbook also mention about that, but that's the contradict to the Bayes postulate. So I cannot explain detail, but I also put some preprint. So your question is, if I put CT as a T and rescale as this one, and then remove the C and the T as just a new time, then we don't need to worry about the C, isn't it? So you may say that dt square.
I mean, C is a function of time, and so C as a function of time and the dt, we can integrate to define the large capital T. Then in terms of capital T time, the coefficient seems to be constant, or in other words, velocity of light is constant.
Right.
That
So
seems, yeah.
So that's against the Bayes postulate, because here homogeneity and isotropy, if I do that way, then usually we can see the anisotropic motion, peculiar motion is introduced in here. So one cannot find the perpendicular time flow against the given hypersurface. So yeah, we cannot go to the detail,
Okay.
but I
I understood your point. Okay, thank you.
Yeah, thanks for question. And yeah, that's also I always ask by people when I talk about this idea. So I also explain with the picture. So I will give you some reference later. Okay. So thanks for question. So 1917. Einstein introduced his static solution, and nowadays, of course, it's written by German, so it's hard to read. But nowadays, people have the reprint in translation version in the English, so you can obtain this one in the archive. So he introduced his static solution, and then he gave up in the 31. So 31 paper, so now is available, translate version is available in the EPJH. And then, so it takes 14 years. And then the reason I thought is people adapt to just invariant of the cosmic, the speed of light when they convert to the static solution to the dynamical one. But whenever we say the invariance of the speed of light means that the C is constant on given hypersurface, means at given time. When we say adapt to the dynamics perpendicular to this hypersurface, then this hypersurface, size of the physical size of this hypersurface is getting larger and larger in Big Bang model. And then their world line is keep perpendicular to the hypersurface at each time. But as you can see, physical time due to the expansion of the scale factor, increasing of the scale factor, physical distance is changed. If you including that effect, then you cannot have the perpendicular time slice by including the expansion effect. So one cannot have the isotropic itself at the beginning. So Bayes postulate always claim that you can find some fundamental observers which time flow is perpendicular to hypersurface, 3D-dimensional hypersurface, which is isotropic and homogeneity. And then only way, consistent way is you should separate the T and the C. So, but yeah, we'll talk about it. The may not this lecture, but one can need to emphasize that one. And then it takes some time. Nowadays, we can, yeah, there's several nice textbook I already showed that how to derive the Friedman robot worker. But it takes some time for the people to how they obtain the robotometric, homogeneous and isotropic space, including the time. Putting the global time is another issue. It's not easy concept, but one should be careful. Special relativity is only true at each time slice. And then put that, this is so-called as a threading in fancy way. Anyway, I need to hurry. I spent too much time. So Big Bang model is, we need to solve the Einstein field equation. That's the GR. So there's no general dynamic solution, but fortunately, Friedman and the Rimetri already, they show that one can use the homogeneous and isotropy in space and then put the dynamic solution. And Robert Walker rigorously proved that one can introduce a metric in that way, in traditional way. Then we can solve the G00 part and then GII part. Due to the homogeneous isotropy, we don't need to separate the XYZ, three-dimensional spatial differences. It's all the same. And then, so there's the information about the co-moving distance is irrelevant. That only involved to our calculation when you consider perturbation. That's the C sigma part, dt. Usually this is constant. It's not changing at all. So that's the background level. If this one is gives in the perturbation case in the local cluster is about 100 kilometers per second, typical size over there in the cluster, but that's the peculiar velocity, not the background level. This is talking about the background level expansion. And then one can have the speed over the background and then acceleration over the background. And then rho is the mass density, which is so it's energy density divided by c squared. And then including the curvature can be Gaussian curvature can be positive, negative, and zero. And then pressure is involved in the when you consider the acceleration of the expansion. And then back to that time, we only known component is a photon and neutrino and the baryon. So people thought this one always give us the positive value. Is one of the Einstein condition, energy condition. So one can introduce so-called as the deceleration parameter to introduce that, because this value will be negative. So they conventionally they put this one as a negative to make the Q itself as a positive. But nowadays, surprisingly, at the very beginning of the universe and the late of the universe, we should have the positive Q instead of a negative, the positive acceleration instead of deceleration. So solution of the Friedman equation is just an expansion universe, so-called as a Big Bang. And then Big Bang is an expectably decelerating expansion universe with ordinary matter. And the Friedman equation itself is in the three-dimensional, is a cosmological principle satisfied, which is also consistent with the observation. People not just adopt it, but based on the observation, universe at the big size is a much, usually even 100 megaparsec is about, usually satisfied, safely we say bigger than 300 megaparsec. Observation shows universe looks like really homogeneous. Isotropy is already proven by the CMB about level as a 10 to the minus 5. Universe is isotropic. But the problem is around the start from the Big Bang, universe cannot, it's hard to have the isotropy. So it's so-called as a horizon problem. And in other way, it looks like the universe is start from the causally disconnected region at the very beginning, but why it's so close to the homogeneous and isotropic today is a puzzle. So it's a problem of the Big Bang. And there's a traditional standard problem in the Big Bang, so-called as a flatness problem or age problem, oldness problem, or fine-tuning problem. Is because based on the observation, the curvature term in here, which is defined as omega k, energy density contrast, divided energy curvature energy term divided by critical energy density, which makes the flat universe. Based on the Planck data, in the most recent one is 18. Planck data is 10 to the minus 3. And if you go back to earlier epoch, based on this equation, in the matter domination epoch and the radiation dominated epoch, this is a 0.1 level close to the critical energy density. But if you go back earlier in the matter domination, then that level should be 10 to the minus 6 plus. So the omega k, omega energy density close to the 1 as in here is today is a 0.1 level. But at that time is a 10 to the minus 6 plus minus 10 to the minus 6. Or if you even consider the radiation dominant epoch, which is, this one is typically for the BBN epoch, which is reachable with the observation, then the critical density even should be even more closer to the 1 by the 10 to the minus 23. And if you go earlier and earlier, then it should get close and close to the 1. So it's kind of fine tuning. We don't know why universe should start from the so close to the critical density at early universe. Otherwise, this term became dominant at earlier, and then we cannot survive. The universe is closed by the dominant term by this one. So that's the age and oldness problem. How we can survive until 13 billion years, so long, like now, at present, without fine tuning. So that's the flatness problem. It's all same language. Another problem is why CMB is so isotropic, because we can think about the Hubble distance, which is the maximum distance can be reached by traveling by the photon, and compare that one to the angular diameter distance. And if you compare two distance at the last scattering surface, then this angular diameter distance is only 1 degree, which is in the solid angle because we are considering as a three-dimensional sphere. Then it looks like the small, we have the 10 to the 4. dA is smaller than the traveling distance by the photon by the 10 to the 4. So we have about 10 to the 4, 10,000 region, which looks like a causally disconnected region. And then if those photon coming from those 10 to the 4 causally disconnected region, then there's no region we see the isotropic CMB today. So one cannot explain why CMB is so isotropic. So we cannot explain how we can adapt to the cosmological principle, homogeneity and isotropy, based on the Big Bang. And the problem of this is coming from the so-called as a Hubble radius. So in the Big Bang, the Hubble radius, which is h is inverse time, so it's the same as the CT. So distance traveled by photon, including the expansion. And in the Big Bang model, the expansion of the universe is decelerating, which means the C over H, so-called as a Hubble radius, is an increasing function. It's a function of time, is increased. Then, as you can see, if you plug into here, the problem in here is if C over AH is keep increasing. It was smaller in the past. So that's why it gives us a smaller and smaller value in omega k, or it's the same in here. It was a smaller size in the past. So good thing is if you increase the C over AH, so-called Hubble radius in the past, is larger in the past. In some period, it's a decreasing function, not an increasing function in the past. Then one can solve the problem of the Big Bang simultaneously. Horizon problem and the aging oldness problem can be solved. So there's several ways you can do it. Eh? You can touch the C, or you can touch the H, the speed. So of course, some people claim that C was larger in the past. So that's one of the motivation of the varying speed of light, but which is not what I mentioned. That's the difference. This is just a theoretical motivation. Another way is you introduce the H is actually getting bigger. So that way is in the past, before this standard Big Bang start from, the Hubble radius is decreased as a function of time. And then now start from so that's the end of the inflation. So that's the so-called reheating. And then universe is follow the Big Bang history, same as in now. So in order to solve the horizon problem, we need to put just a constraint as the initial Hubble radius is as big as the present Hubble radius. Then every patch, every source of the photon is coming from the same size as today. So that's why at least the same size as today. So that's why we can see the isotropic, the CMB. That's the solution for the Big Bang. So there's a nice introduction. There's a nice the ideas about the inflation. So also some people try to use the varying speed of light or bouncing universe, but I will not cover this one. And we just focus on the superluminal expansion at the early universe to make this the large enough size of Hubble radius at the beginning. So that's the early inflation. So how much inflation we need is actually that's what I show. And if you just follow the algebra, then you see that at least we need 64. This is a minimum number. It depends on the energy, what energy scale you put in. So it can be start from 50 or 55, but 64 is a traditional way, more conservative value. And bigger than that is okay. It's a minimum requirement, isn't it? If one can start from the larger patch, then of course we can have the isotropic signal. This cartoon is some complaint from the cosmologists, so-called cosmologists, because after the inflation, it's more or less like the particle physics. So this beggar is say I was the cosmologist based on you may think about the astronomer based on observation and etc. But after the inflation, particle physicist became so-called as a cosmologist, and he just loses his job. So this is just a funny cartoon. So now this detail will be covered by Professor Gong, so I will not talk about too much because I still have some time. But in order to have the satisfied scenario, we should start from the slower condition. So it can be start from here, but this one is also looks like steep, but you may think that this one can have take some long time, slow. So there's two kinds of types, slower the inflation to make the second phase transition. First phase transition, including the creation, the bubble is nowadays is against the observation, so usually it's a second order. So there's two scenarios, so chaotic and usually slower. And then after they reach to the minimum, it can be rapidly oscillate. So that gives us the so-called reheating. So there's a nice traditional textbook and then the papers, so one can read for that. But today I'll just focus on this single scalar field with the slower. So we just focus on the single field inflation. Then the only thing we need to know is just the energy. So it's better to say energy density and the pressure and field equation itself, including the acceleration and the velocity. And slow roll condition can be converted to the so-called as a slow roll parameter by using the field equation with the slow roll condition. Slow roll means that it's dominated by potential and kinetic energy. It's slow, so the kinetic energy is much bit smaller than the potential energy. Then one can have the two slow roll parameter. One can even have the more than that. But in the theoretical side, it's not convenient to use this field equation. One can specify the inflation by its potential form. So it's better to use the parameter based on that potential, derivative of potential. And then one can obtain those values, these parameter values based on the observation. If one can find that value from the observation by translating to the so-called the power spectrum, then one can plug that to extract the theory, which means the form of the potential, the first derivative and the second derivative. So it's a nice way to obtain the theoretical prediction from the observation later by measuring the power spectrum. Okay, so I should rush. I have only 10 minutes left. So Leading is still arguable, but just you have a rapid oscillation, and it should be have to finish the inflation. So that will be entropy generated, huge amount of entropy generated during the reheating. And so also there's also the gravitational wave generated from the tensor perturbation. We have the scalar perturbation and tensor perturbation. And instead of transverse and transverse and the TT gauge, it's better to use the combination of the plus and cross mode, which give us the helicity, which is close to the observation. Then this helicity to combination of the plus and cross generated by the inflation can be observed to the scale of the perturbation. That's a so-called as a two-point correlation, but after you change it to the Fourier transform, this one is, we can say, it's a power spectrum. And then I hope the Kong will be covered about how we can obtain this one. And this is a dimension of the length cubic. So one better to use is a volume. So usually one use the introduce the dimension is this is the volume unit dimension. So one use the dimensionless case and then introduce that one as a power spectrum. Dimension is a power spectrum, including the amplitude, only specified by the amplitude and pivot scale and the spectral index. So one can compare this one from the various observations, especially for the tensor mode, it should be coming from the B mode polarization, because the Thomson scattering can only produce the scalar one. So and also the scalar perturbation can be specified the curvature perturbation, and one can do the same thing for the scalar dimensionless power spectrum, can be specified by just phenomenologically, we can interpret in this way. And also one can compare this one as a temperature CMB anisotropy, also from the metal power spectrum. So in that way, because so far Planck cannot measure the B mode polarization. So in order to have the information about the tensor mode, one should include the bicep CAC array. It's a 15. This is the Planck final result in the 18. So one can extract the information about the NS and NT, which is related to the slower parameter, and also the ratio, tensor to scalar ratio, which is also related to the slower parameter. So because of this relation, one can think about the potential form for the various inflation potential. And then you can see the marginally satisfying model, and then the best fit model is usually is the Starobinsky model here. So you can see. So that's how one can get the inflation to use the prediction. So now, thanks to the inflation, now the cosmology became a really the predictable theory. Previously, cosmology is based on the observation, astronomy, and one can just try to fit something just based on the observation. But inflation makes that one can expect and predict large scale structure and CMB anisotropy. And those cosmological perturbation is statistics, and that means that everything should be we interpret as the ensemble. But in reality, the ensemble average is just theoretical. But in reality, what we need to do is we need to get the information based on the space. So there's a gap between the theoretical calculation and the volume integral. That's the so-called as a cosmic variance. So if the volume can be infinite, then expectation value, ensemble expectation value can be reached to the 0. That's the so-called as a algorithmic theorem, which means the ensemble average is the same as the volume integral over the correlation function. But there's the gap because in practical, based on the observational limit, V is finite. So this cannot be the same. So that's the so-called as a cosmic variance. So that's usually the problem, systematic problem in the large scale observation, both in the matter power spectrum and the CMB. And also, real calculation is done in the configuration space, but the theoretical calculation is done in the Fourier transform, Fourier space. So one can also need to be guaranteed that the random field transform of the random field also should be the random field. And we just assume that in the reality of the random, the Gaussian field. And then everything, if everything is based on the quantum generation, then means the probability is Gaussian. So then only 2-point correlation is important. Odd number of the power spectrum correlation is 0 in the Gaussian distribution. So that's why we only need the 2-point correlation function or transform over that the power spectrum, including the every information we need. But if not, that's true for the single field inflation. But of course, there can be some more general case. Then one can need to worry about also the 3-point function as a bispectrum, and one can check for the non-Gaussianity over that. There's several types of non-Gaussianity, but the local type in the based on the observation is very small. So usually it was a hard issue before, but nowadays not that many talking about, not many people talking about the non-Gaussianity. So we have the observable quantity, the temperature fluctuation or the matter fluctuation, which is all coming from the curvature perturbation, and which is related, if you adopt the inflation model, then it can be plugged into the inflaton field. So theoretically, and Professor Kong will talk about this process, and this is theoretically clear. But when that generator propagate to us from the generation epoch, they went through all the background evolution, which is involved to the so-called transfer function, which is a complicated mechanism involved here. That should be function of time and function of scale. The progenitor is only fixed value at a given time, so it's constant as a function of time. But the observation is done based on the time, and every information should be involved into the transfer function. So it's a complicated. So we see the matter power spectrum. So this is coming from the CMB, which is consists, because in the matter power spectrum, one cannot measure this part due to the observation. So systematic problem in here, but one can obtain the information for the large scale from the CMB. And then there's the turnover happening here, and BAO wiggle in showing in here, and then nonlinear region. And there's also numerical simulation should be going in. And there's a complicated, so only region we can prove in here is a linear region around in here. Quite limited area from the wave number. So let me, because I will talk about this on Saturday, so let me skip. So as of
in your couple of pages before, when you talk about the spectrum and the peak, are there some way? Oh yeah, here some simple argument why the peak occurs that scale? Are there some simple arguments?
You mean the peak in turnover scale?
Yeah, turnover. Yeah, why turnover occurs that scale?
From here, before turnover is a radiation dominated, so matter cannot grow. After the background universe is matter dominated, from the scale, now matter started to grow. This is pressure dominated in the radiation dominated epoch. In the matter domination, the gravity overcome the pressure, so it started to grow. So that behavior happened at the turnover scale in here is an equivalent to epoch when the matter became dominant than radiation. So this shows the growing behavior. So yeah.
Okay,
so
thank you.
if one can measure this one, it also gives us the very important information about how many relative spaces can be there and etc. So this great information.
So very naively, if meta domination occurs later and later, rather recent period, then the peak, the turnover will be shifting to the right or left. I mean, how does it?
So one is the C over AH is a Hubble radius traveled by the photon. So it's an inverse length, is a wave number. So this one is a K is the wave number. So if the ACH is became the larger, then K became smaller.
I see. Okay.
The larger scale, and vice versa. So you can.
Okay. Thank you.
Okay. Okay. So this will be covered Saturday. So let me stop because now I have only few slides and time is already up. So let me emphasize several things. So when we talk about the cosmology, then minimum size is a cluster, it's a megaparsec, which means about 10 to the 43 kilogram. If it's smaller than that, then usually it's plasma physics, so it's astrophysics and astronomy. So galaxy scale, when someone talking about the individual behavior of a galaxy, is out of the gravity. Numerical simulation based on the galaxy behavior in the numerical simulation is based on the plasma physics. It's nothing to the gravity is a subdominant. So simulation and observation is can be deviate from the lambda CDM, and it's not a strange thing. Only lambda CDM is consistent in the large scale. in the at least the megaparsec and 100 megaparsec. In the galaxy scale, deviate from the lambda CDM is not surprising. It's okay. So we will show the several observations, and we may think that this is a real universe, but this one should be proved by observed universe. But observed universe, due to the resolution of the telescope or the contamination, like this in the CMB mode, there's the dust and periphery and synchrotron. Those are the contamination is always included in the observed universe. And resolution, one cannot maybe, and our observation may not have distinguished the color with the cow. So it gives us that only the rough shape is can be consistent in the real universe. But from the observation, we may interpret this one based on we can interpret in the observed universe, and then this is an analyzed universe. And we say now it's around 95% consistent, because in those observations, we never say about the cartoon of the tattoo of the cow or color, we may don't care, or even the heading of the head, the direction of the head doesn't care. Its overall shape is okay. Then we say it's 95% consistent. But maybe it's better to say that if someone say too much detail about the observed universe in the analyzed universe, because we don't know which contamination we should remove correctly. So this is too much detail, and then it looks like very close to the original one. But if we allowed those systematics and which cannot be overcome, then our analyzed universe is roughly shaped only at the 68%, 1 sigma level accuracy. But nobody knows which one is more close to the real universe, this one or this one. Someone talking about the shape of this one and say, oh, it's very close to the real one in here, and analyze one, and then say real thing is in here, is this one. But it may not. We may not have the lag in our analyzed universe, but because that's not due to our ignorance or the problem, but it may due to the systematic itself based on the observation or theory. So even though we try to combine too much detail from the different to get the information about the sterile neutrino or modify the gravity from the the supernovae and the CMB from the extra sterile neutrino and etc. We may combine all those things, and maybe we have some even crazy idea about the real things. So we should be careful about what's the limitation of the observation and the theory, especially in systematic. And it may better keep in mind that. So we cannot say theory can prove anything, but sometimes we only can disprove that. So yeah, let's keep in mind that one, and that's the end of the talk of today. Thank you.
Okay. Yeah. Thank you for giving a nice introduction and the review on Big Bang and inflation. Okay. So any comments or question? Do you have any comments or question? It's almost 11, so I guess that after ending of this session, you could ask anything and comments. Okay. Thank you. Yeah, let next speak again. Okay.
Thank you.